Last image will show you conceptually why an integrating mode phase interpreter can achieve high linearity easily. Therefore, the IMPI may provide enough phase resolution for very small bit period data over a very high-speed SerDes. Is that a true statement? Yes or no? The most critical one is the duty cycle in most high data rate SerDes. So, we need to look into why IMPI with inherent 50% duty cycle for high-speed SerDes is in demand. In most high data rate SerDes, even though 32 gigabit per second, the clocking duration and clocking distribution are very challenging to achieve a low jitter and low power operation at the same time in a full rate topology. Therefore, people tend to apply the half rate clocking like 16 GHz for 32 gigabit per second in most SerDes. Even the half rate clocking has a reasonable jitter. A final time resolution from an IMPI is still needed for good timing budget without violating the setup and hold time at the flip-flop. By the way, we'll talk about the high-speed flops later after getting Seth's good suggestion. So far, from the serialization image of the half-rate clocking, you should realize even though the timing of the flops was good without any big error, the duty cycle distortion DCD may introduce the even R jitter at the TX output, which is sending to the RX input, so that the RX sampling timing may not have enough margin and to cause big error. What's more are the RX sampling changes? Think about the sampling and reset image for 5 seconds. Great. The strong arm latch sampler is the most popular in high-speed SerDes since it has a high sensitivity and low power at the same time in the clock sampler category. But both the logic high and logic zero level of the sampling clock will be very critical for the entire operations for the sampling, rejection, and reset phases respectively. Correct? If yes, does the sampling clock's duty cycle for the sampler must be 50%? Think about the transistor sizing images for 5 seconds if the duty cycle isn't 50%. Bingo! Unlike the TX even R jitter from the half-rate multiplexer or serialization, the sampling clock's duty cycle for the sampler can be anything. For example, if the clock duty cycle is 25%, how would you design the sampler? Yes, you may have more time for the reset state, and you would like to make a weak pull-up PMOS with a smaller transistor size. On the other hand, you may want to increase the strength on those input differential pairs and cross-couple pairs to resolve the correct logic quickly during the limited 25% clock period time. Then I will leave the 75% duty cycle of the clock for your exercise of resizing the sampler again. Okay, if the clock duty cycle does not matter, what should I bring it up now? Think about the subtlety image for 5 seconds. Yes, the constant duty cycle does matter, since you only size once for either a low duty cycle or a high duty cycle. Therefore, the sampler must be clocked with a constant duty cycle during different phases from the IMPI. Otherwise, the sampler would have a timing variation or wrong output data at some varying duty cycle when the input data goes higher and higher. Then the whole closed loop in either a clock data recovery CDR or decision feedback equalizer DFE would result in a nonlinear phase selection because of the duty cycle, even though the rising edge phase of the IMPI is pretty linear as a high resolution phase spacing. So we must have a constant duty cycle for the sampler over different phase codes, such that the high linearity of the rising edge phase would be meaningful. After understanding the need for constant duty cycle reasonably in a clock sampler, then if we review the full operation of the last IMPI one more time, you may realize what can be improved. So, to help you create your innovation, can you pause for 5 seconds and look at the falling edge image closely? Very good. The fundamental issue is the single edge interpolation with the hard reset in region 3. Therefore, either the PWM outputs after the slicer or the DCD will depend on the interpolation cost or strength. Without adding complicated DCC with an extra power overhead, you can simply change the single edge interpolation to a dual edge interpolation. Instead of discharging the capacitor for the reset pull down, the beauty of the symmetric integration may reuse the discharging with the falling edge interpolation, including the retention state. The interpreted waveform can already be near 50% duty cycle. Even adding extra DCC after it to make a clocking in a perfect 50% duty cycle over PVT, the power overhead of the DCC should still be little. If the waveform image of the dual edge interpolation is so simple, can you provide the innovation of your circuit image one more time by thinking about the current source image for 5 seconds? Bingo! The previous single edge or rising edge interpolation needs 2 PMOS current source for ramping up the varying and constant slope respectively for another falling edge interpolation. Adding the extra 2 MOS current source for ramping down should be a straightforward circuit image of your innovation. As the initial IMPI, the input clock phases V5 in 1 and V5 in 2 would still control the top and the bottom current sources. Then the remaining S1 to S4 switches would control the current flow of the current source into or out of the Vint node, which determines the interpolation factor from the selected phase code. To make sure the integration works in the right angle state machine, the S1 to S4 is generated by the selection state S_I of each cell and a logic feedback signal VFB from the Vint node. So instead of a complicated deck to tune the current source precisely, a simplified slicer-based IMPI unit can simply achieve a 7-bit phase resolution by the 128 unit interpolation cells. Besides the interpolation cells, how to retain the state through the retention cells? Yes, just reuse the same interpolation cells but apply different control logics. Then we can connect both interpolation cells and retention cells at the vint node, but let both cells be enabled exclusively. For example, in regions 1, 2, 4, and 5, the R signals cut the signal path from the retention cells to node vint, thus isolating the IMPI from the retention cell, and the IM works properly. In region 3 and 6, the S signals disable all the control transistors in the IMPI, but the R signals connect to the node vint to the retention cell, providing the desired logic voltage level to the vint node. Thus, S and R signal keep changing during the different regions or different modes respectively, such as the interpreted waveform at vint works properly from region 1 to region 6 in a 1 clock period. Here are the summarized images showing you why an IMPI with a 50% duty cycle for high-speed SerDes is needed. In the TX half-rate clocking simulation operation, we demonstrate a non-50% duty cycle causes the even R jitter at the TX output, which is the RX input. Then the link still has a lower timing margin, even though the TXI may have a better timing margin owing to the high linearity, high phase resolution PI. In addition, the original DCD of the single edge IMPI may cause the varying duty cycle over different phase codes. Then, the varying duty cycle may cause less timing margin at either the RX CDR or RX DFE. So, we must add a duty cycle correction after the previous IMPI. But that adds too much power and design overhead. The easiest way is to replace the single edge IMPI with a dual edge IMPI, in which people propose a few different approaches. In this reference, they applied a simple sizer-based IM and RM to achieve a high linearity IMPI and a 50% duty cycle at the same time. Of course, this approach of the dual edge IMPI may still have some limitations, and we may think about how to improve it together next time. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.